Welcome back to Mechanical Engineering Made Simple. Show your support with a like, a follow, or a comment. Let's keep leveling up together. Welcome to the deep dive. We've got a fantastic set of resources you sent over, all focused on shafts and the reliability of rotating equipment.
It's a great topic.
It is. So our mission today, in this deep dive we're calling Shafts That Don't Fail, is to really break down those critical design decisions.
The ones that really separate the equipment that just sort of works from the equipment that truly runs forever.
Exactly. We're talking about the foundational stuff sizing, materials, fits, everything that goes into making a shaft robust.
It really is the spine of any rotating machine. A pump, a mixer, a turbine, it all comes back to the shaft. So we have to get this right, from the big picture of sizing all the way down to the tiny details of surface finish.
Okay, let's jump right in then. Let's start with what has to be the biggest question for any designer, especially when they're new to this.
I think I know where you're going.
How do I choose the right shaft diameter? Because if you look in a textbook, it feels so simple. It looks like it's just torque divided by allowable stress.
And that is the classic trap. That calculation, it's not wrong, but it's dangerously incomplete.
It's just the starting point.
It's the bare minimum for strength, under like a perfect static load. But the real world is never that simple. The diameter has to satisfy a whole system of constraints, and pure strength is usually the easiest one to meet.
So if that torque check is just our baseline, what else is hitting the shaft? You've got the weight of rotors, impellers,
Dynamic process forces, axial thrust, all of it. Suddenly you're not just dealing with simple shear. You've got a complex mix of axial, shear, and bending stresses happening all at once.
and that simple math goes right out the window.
Completely. You have to start using more advanced methods, like von Mises criteria, to figure out what the true effective stress is inside that material. Our sources are really clear on this. If you have bending and torsion together, the basic formulas can lead you to a catastrophic failure.
Which brings us right to material selection. This isn't just about picking something strong enough. It's about getting a material with the right baseline yield strength to handle all those combined stresses.
Precisely. And this is where we move beyond basic mild steel and get into the alloys. For the really heavy-duty stuff, I'm talking extreme loads, dynamic impacts, the sources all point to high-performance alloy steels.
Like 4340, 6150, those kinds of materials.
Exactly. 4340, 6150, 4620. These are your nickel, chromium, molybdenum alloys. They're engineered for high strength and, just as importantly, toughness under repeated loading.
And what if it's, say, a critical transmission shaft, something with high torque but maybe less extreme impact?
Then 4140 is the immediate go-to. It's the workhorse. Great strength, great hardness after heat treatment, but the big takeaway isn't just a number. It's realizing that your material has to support the most complex stress state, not just the highest torque.
That's a great point. You underspend on the material, you're forced to make the shaft enormous just to keep the stresses down.
And that has its own problems.
It does, which is a perfect transition, actually. Let's talk about those localized dangers. Why do shafts almost always seem to fail at transitions, like a step in diameter, instead of in the straight, uniform section?
It's all about geometry. A straight section carries stress nice and evenly. But the second you introduce a change of step, a keyway, a groove, you create what's called a stress concentration.
It's like a focal point for all that force.
It's the mechanical equivalent of starting a crack. The sharper that corner, the more the stress gets magnified right at that point.
So we quantify this with the stress concentration factor, Cajun.
Yes, and that Kate factor tells you how many times higher the stress is at that spot compared to what you calculated for the main body of the shaft. For fatigue, these stress razors are everything. They tell you exactly where the failure is going to start.
Even in a ductile material like 4140.
Absolutely. So the fix isn't complicated, but it's crucial. You use generous fillet radii, you use smooth tapers, you avoid sharp corners at all costs. It's the geometry, not just the raw diameter, that dictates the fatigue life of that shaft.
Okay, so we've managed the geometry. Now we have to actually put a bearing on this thing. What's the deal with tolerances and fits? We know the inner ring needs an interference fit to stop it from spinning on the shaft.
Right. The goal is to prevent what's called creep, but interference doesn't mean you just jam it on there with a bigger hammer.
It has to be controlled.
It has to be very controlled. Too much interference, and you can actually overstress and damage the bearing's inner ring, which kills its fatigue life. Too little, and the bearing creeps, causing wear, and the fit fails anyway.
Which is where standards come in. The sources mention the ANSI standard force and shrink fits, classes FN1 through FN5.
And that's essential. It brings us to that alphabet soup of tolerance notation you see on drawings, like 45H7P6.
That code isn't random.
Not at all. The P6 part defines the shaft's tolerance range. It's usually +0 and minus a very small number. That guarantees you get the right amount of interference, not too loose and definitely not too tight.
So the practical rule here is avoid oversized shafts. An oversized shaft completely destroys that carefully engineered fit.
It's one of the fastest ways to kill a bearing. And we can't forget about surface finish here either.
Ah, right.
The roughness of the shaft surface, what we call raw, directly affects how well that fit holds. If the surface is too rough, those little peaks and valleys get crushed when you install the bearing, and you lose your interference over time.
So even with the perfect H7P6 tolerance, a bad surface finish can undermine the whole thing.
Exactly.
All right, let's shift gears to the dynamic battleground. This is where I think a lot of mistakes happen. Is deflection really more important than stress?
In so many critical applications, the answer is a huge yes. Especially things with mechanical seals or long mixers. Your stress calculations could show a safety factor of 5, but if the shaft bends too much, the system is going to fail. Period.
And what's causing that failure, if the shaft is technically strong enough?
It's all collateral damage. Too much deflection causes bearing misalignment, which just chews them up. It causes massive vibration. And, the big one, it causes seal failure. A mechanical seal might have a gap of a few thousandths of an inch. If your shaft deflects 10 thousandths, the seal is gone.
So the limits from the seals and bearings become the real design driver, not the stress.
They become the governing constraint. And that's why we start talking about rigidity. If you look at the beam deflection formulas, you'll see rigidity is controlled by the material's modulus of elasticity, E, and the moment of inertia, I.
And since E is basically the same for all steel,
It all comes down to I, and I is proportional to the diameter to the fourth power.
which is the engineer's secret weapon.
It's the secret weapon. A tiny increase in diameter gives you a massive boost in stiffness. You might double the shaft's diameter just to meet a seal's deflection limit, even when the stress was perfectly fine at the smaller size.
That's a great insight. Now, if deflection is the systemic failure, what about fatigue? How does dynamic cyclic loading change the game?
Fatigue is what defines whether a shaft runs forever. Any rotating shaft sees repeated bending and torque cycles, and it will fail from that repetition long before it ever reaches its static yield strength.
This is where the endurance limit comes in.
Right. The endurance limit is the highest stress level you can repeat, basically indefinitely, without causing a failure. For steel, we usually say that's around 10 million cycles for infinite life.
But getting there is complex. The sources list a ton of factors: material, heat treat, geometry, surface condition.
All of them matter. We already talked about geometry, the KT factor, but the ones that often get overlooked are surface finish and what's called the size effect.
What's the size effect?
It's a bit counterintuitive. A large diameter shaft, even made of the exact same material, often has a lower endurance limit than a small test specimen from a lab. You have to account for that reduction when you're designing something big.
Wow. And the surface finish?
A poor surface finish, even on the best alloy steel, is like having microscopic cracks all over the part. Each one is a little stress razor, ready to start a fatigue failure. You could spend a fortune on 4340 steel and then ruin it with a rough finish.
That's incredible. Okay, let's talk about the silent killers. The things that happen even if the design is perfect. Do you really need to balance shafts in low-speed equipment?
Yes, absolutely yes. That is such a dangerous myth that balancing is only for high RPM machines.
What's the logic there?
It's the difference between static and dynamic unbalance. A shaft can be perfectly balanced when it's sitting still. That's static balance. But if the mass isn't distributed evenly along its length, it will create a wobble when it spins. That's dynamic unbalance.
So even running at, say, 100 or 200 RPM, that constant wobble is still doing damage.
It's a constant cyclical load on the bearings and the frame. It accelerates wear, it increases vibration, and it shortens the life of everything. Dynamic balancing is about maximizing life, regardless of the speed.
Okay, that makes sense. Finally, let's talk about the last mile, installation. You can have the perfect design, the perfect material, perfect tolerances, and it can all be ruined in the last 5 minutes.
Installation is the moment of truth. I'd say our sources are clear that installation errors are probably the #1 cause of premature failures in the field.
What are the big mistakes you see? The war stories.
Oh, the classics. Bearings being pressed on crooked, which creates instant misalignment. Not cleaning the shaft or the housing, leaving burrs or dirt that prevent a proper fit. Tightening locking collars in the wrong order, which can actually bend the shaft slightly.
Little things that have huge consequences.
Huge. A bad installation introduces all these unintended loads, preload, axial forces, misalignment, that the design never accounted for.
Which really circles back to the design validation. Your job isn't done when the drawing is released. It's done when you know it can be assembled correctly.
Exactly. If your installation procedure allows for error, you've basically undone all the hard work you put into the design. Installation either validates or invalidates everything.
We have covered so much ground here. We've really dug into this complex system of constraints that defines a shaft that won't fail. It's this delicate balance, isn't it?
It is. It starts with the right material, like a high-performance alloy. Then you control the geometry using those big fillet radii to defeat the KD factors, and you make sure it's stiff enough to handle deflection, which, as we saw, often matters more than strength.
And all of that is built on a foundation of dynamic performance surviving fatigue for millions of cycles and being properly balanced. It's all secured by precision manufacturing and finally, correct installation.
Exactly. So for your next step, here's something to think about. We saw how critical surface finish is for fatigue life and for a good interference fit. So how much does improving that surface finish, let's say going from a standard machine finish to a precision ground N6 or N7 finish, actually improve the fatigue endurance limit of a highly stressed part? And where does the cost of achieving that superfine finish intersects with the complexity of also holding a tight dimensional tolerance, like for an H7P6 fit? That trade-off between surface precision and dimensional precision is the next layer waiting for you on your deep dive.